but can only be transferred from one form to another. So if we go to this situation here where we've got a skateboarder on a parabolic ramp, and he's 6 meters above the ground there, then if we set him in motion, all the potential energy that he has at 6 meters above is going to be converted to kinetic energy as he goes down the ramp. So as he goes down the ramp and we bring him back here, that's where all the potential energy he had here will be converted to the maximum kinetic energy that he has there. And then as he goes up the other side, the kinetic energy is going to be converted back into gravitational potential energy again. So if we put him back up here, you can see that he reaches a maximum speed, and therefore his kinetic energy is maximum at the trough here. So the potential energy that he had is being converted to kinetic energy, and this can keep going all the way through. The question is, how do we calculate the potential energy he has, the kinetic energy he has, and then how could we calculate the speed ourselves that he has? We would have to know what his mass was to be able to do this. But the first thing you need to know is that if this was a frictionless surface, he would just keep doing this over and over again. Of course, in a real world situation, this doesn't happen. So I'm going to stop him when he gets to the top, take him back up to the top, just leave him there for the moment. At that 6 meter height, let's say he's a 80 kilogram skateboarder. So we can calculate his gravitational potential energy. So the skateboarder is 80 kg, and he is 6 meters above the ground. So if you remember the other day's lesson, we can calculate gravitational potential energy as being equal to his mass times the gravitational acceleration, and that's the force, times the height he is above the ground. So in this case, it's equal to 80 times 10 times 6, and 6 times 8 t must be 400, and 80, and therefore his gravitational potential energy is just going to be we can just use the calculator here. So 80 times 10, that's 480, times 6 equals 4,480 joules. So his potential energy at the top of the ramp is equal to 4,800 joules. And remember, joules has to be with an uppercase I. Now, when he comes down the ramp, at this point here, right there, that's where he reaches his maximum velocity, and we can see that. We'll take him back up, let him come down, and you can see that he reaches his maximum velocity right there when it coincides with the trough. So at that point here, all the potential, everything. So the potential energy's gone from 4,800 to 0 there, but that is now equal to his maximum kinetic energy. So from start to bottom of trough, all the gravitational potential energy is converted to kinetic energy. Another way of looking at that is to say that at the top he's got 4,800 joules of potential energy, but no kinetic energy. That's important. So at the top of ramp, he has 4,800 joules of potential energy, gravitational potential energy, and 0 kinetic energy, because he's not moving there. For that brief moment in time, he's stationary. However, when he gets to the bottom, it's the other way around. All the so he's going to have he will have 0 potential energy and 4,800 joules of kinetic energy. And we can use that to calculate what his maximum speed is. Remembering yesterday, kinetic energy is equal to half the mass times the, so equals 1/2 the mass times the velocity squared. And so we can do the calculation that you were supposed to be able to do by the end of class yesterday to calculate this speed. So it should equal 1/2 80 kg, and we know that this was 4,800 joules. So, and this is times velocity squared. So if we now do our math, rearrange the formula, and divide 4,800 by 1/2 of 80, which is 40, we can get the answer to what v squared is. So we can just put this in. So we're going to have 4,800 divided by 1/2 of 80, which would be 40. And we probably should be able to do that in our heads, actually, because you cut the zeros off. So it's going to be 120 equals v squared. So equals v squared, and so we can just check it with our calculator. We can divide that by 40 and it equals 120, and if we take the square root of 120, then we can find, so we can go ahead and do this. So the square root of 120 is going to equal V, and that would be equal to just under 11 actually, because 11 11s would be 121, so this would be 10.9 meters per second, thereabouts. You can use your calculator to find out the exact answer, but that would be equal to V. So that's how we can use gravitational potential energy to find out kinetic energy. But more importantly now, if we go back to this and we put them up here, we can find out what his speed would be at any of these points by just knowing how much his potential energy changed. So how much potential energy would he have there, then the difference in those two would give us the energy that's been converted to kinetic energy, and we could then do the same process, and then we could do the same when he gets down to 2, and you'll get surprised. It's not a because of the squared nature in the formula, it's not actually a linear or halving, because it would be if his mass was halved, but that's not the case. So potential energy at top of a ramp equals 4,800 joules. I don't need to do that calculation. Potential energy, and I'm talking about gravitational potential at 4 meters, equals the mass, which is 80, times 10 times 4, equals, so let's do that, that's 800 times 4. Again, we can do this in our head really. So that's 3,200 joules. The difference, so 4,800 minus 3,200 is equal to 1,600 joules. So 1,600 joules of potential energy has been converted to kinetic energy, is what you have to remember here. So 1,600 joules of potential energy is converted to kinetic energy. So we can go ahead and do the same calculation we did over here. I'm just going to now copy that and put it in here and do the calculation. Just change the figures. So this will be actually now 1,600. It will be 1,600 here. $1,600 divided by 40, and that's just going to be 40 in this case. Yeah, it will be 40. Don't need to do that one using the calculator. That's going to be 40 there, and the square root of 40 is approximately 6 point something or other. 6 sixes are 36, so about 6.4 meters per second squared. So he's gone from here 10 meters per second squared to 6.4. And then if we were to do that one more time for the 2 meters, so he goes from there to there, so we can go ahead and do that again, just to give you the idea of what's going on here. So now at 2 meters, the gravitational potential energy is going to be 800 times 2, which will be 1600 joules. The difference is going to be now 3,200. Yeah, that'll be right, 3,200 joules. So 3,200 joules of potential energy has been converted to kinetic energy. So this is going to be 3,200. This here will be 3,200. That's going to be 80. Because cut the zeros off, that'll be 4 goes into 32, 8, so that'll be 80, that'll be the square root of 80. And the square root of 80, 8 eighths is 64, and it's not quite 9, because 9 nines would be 81, so there will be 9.1 meters per second squared. Now, if you're thinking along the line, there's a mistake in here, because this would be at the bottom here. This would be at the bottom of the... So actually that's correct. At the bottom, so he's gone from no kinetic energy at the top to 6.4 meters per second to 9.1 meters per second, and then to 10.9 at the bottom. Okay, and that's just utilizing the conservation of energy. So you could do that anywhere on that graph. Now, if we switch to this one and we put them in here, if we let them go, you can see what happens here. So all his kinetic energy is converted to, all his potential energy here is converted to kinetic energy there. It's converted back to potential, some of it's converted back to potential energy there. But note that he's got maximum kinetic energy here, potential energy there and there, maximum kinetic energy here, and these two pieces in here must add up to what the kinetic energy is down here. So that is the conservation of kinetic energy. Now if I go back and use a different simulation model, and let's use the pendulum here this time. So if I use the pendulum simulation, the same thing applies here. There's like a swing. So in the swing, which is one of the questions in your SciPad that goes with this. So we just got to wait for this to load. So here's the introduction. So if I take this back up to right up to here, and you can see that there's a meter from top to bottom. And I let it swing, then the same principle applies. He's going to have maximum potential energy there, and minimum potential energy and maximum kinetic energy there, and the same up here. And we're just going to keep this at Earth, so we could go ahead and actually calculate what the maximum energy is up the top. We've got a 1 kilogram weight there, and we've got 10 meters per second, so his potential energy at the top would be 1 times 10 times 1, which would be 10 joules of energy. All that 10 joules of energy is converted to kinetic energy there, and just as in the other example, we could do the same calculations here. So in fact, we could go to this, we could use the same thing. So at the top of the pendulum, he has, and we'll calculate that in a minute. We can calculate how much, we can calculate his potential. He's going to have 1 times 10 times 1 equals 10 joules of potential energy and 0 of kinetic. At the bottom of the ramp, it's going to be the other way around. He's going to have 0 joules of kinetic energy, of potential energy, and he's going to have 10 joules of kinetic energy. So we can now change this to 10. This was 1, so this will be 10 divided by 0.5. That's going to be 20. So v squared equals 20. The square root of 20 will give us the speed that he would have at the bottom of the pendulum, and the square root of that of 20 is 4.45. So if we take him up there again, so these are the sorts of things you can do. Again, this is assuming frictionless surface as it was in the other example. So I'm going to stop this. You've got a calculation very similar to that about a ball. So we'll go back to a new simulation. In this case, we can talk about this ramp. Again, this is only to help me do this presentation for you. So I just got to wait for this to download, and then I've got to get it to go. The internet has been a little bit slow here tonight. Let's get going here. The point being is that in a ramp, if I go back here and put a new slide in, just a new one of these, and put ramp, and I put in a shape instead of shape, this is a question that they really like to show or to talk about so here we have a ramp, and let's say it's 1 meter high here. So I'm going to put in 1 meter. So I'm going to make this 1 meter here. I can just go, if I was thinking ahead, I'd have all this sorted by now. So here's a text box. I can put a text box in here. Let's make it 10 meters. Right, so the ramp here is 10 meters. Let's make the so that's the height of the ramp. Let's make the length of the ramp 20 meters. So this length down here is 20 meters. Now we can put a ball in here, and this ball can be lifted from the ground up, or it can be pushed. So let's say this is a 20, let's say it's a 10. Let's say the ball is a 10 kg ball. So we can have that 10 kg ball and we can either push it up the ramp or we can lift it up the ramp. The interesting thing here is that the gain and potential energy is the same in both cases. So in fact, the amount of potential energy that this ball gains, so E P is equal to the mass of the ball times the gravitational acceleration times the height it's going to get lifted. So it's going to gain, no matter which way you put it, 10 times 10 times 10. Because the height that it rises is 10 meters, even though it's going up the ramp there. And you shouldn't get confused about the gain and potential. The gain and potential energy has nothing to do with the length of that slope there. So it's equal to 1,000 joules of potential energy being gained here. The thing is, you would not have to put in as much force to get it to going up there as you would there. Because if we took work done is force times distance. So for the guy lifting it from there, he actually has to put in this amount of energy to lift it. So 1,000 joules has to equal the force he uses times the distance, which is 10 meters. So this is going to be here, the force is going to be 1,000 joules divided by 10. Divided by 10 meters, and that's going to equal 100 newtons force. So the guy lifting it straight from there to there has to be a pretty good weightlifter, because he's going to use 1,000 newtons. But the work done the other way is simply going to be 1,000 divided by 20, because the distance he has to push it up the slope is 20. So 1,000 divided by 20 equals 50 newtons. So you get a mechanical advantage by lifting it up, pushing it up the slope, because the distance you travel is further, but the amount of energy gained is the same. So we can get the same thing happening here. Okay, I'm not going to be able to run that simulation for you, but I hope that shows you a little bit about the law of conservation of energy.